Right, the first of our standalone, I guess, extension topics for the HSC course. So, vectors. Sometimes the word vector sometimes strikes fear in the hearts of some people because they think, oh, vector. But it's just a fancy word for array. So where we're going to begin with vectors is actually where we just left off, and that is the translation of graphs. I think it's a useful way of introducing the idea of vectors. So what we've been doing is we've been getting things like a parabola and translating it 2 units to the right and then 1 up. What's the new equation of the parabola? So there's our original parabola, shifted 2 to the right, 1 up. There's our new parabola. But we did that with 2 moves. We could have done it with 1 move. Instead of going horizontally and vertically, I went diagonally. So all right, with 2 moves, I went from x squared, it became x minus 2 all squared, and then I moved it up and it became x minus 2 squared plus 1. But if I combine those horizontal and vertical translation, voila, into one translation, and now I'll just use the fancy word, vector. Okay, and that's what we call a displacement vector. We're displacing the point where it originally was to where it's going to. And the beauty of using vectors is every single point can be done like that. So I could, theoretically, every single point, I could move it in the same direction and eventually I'd end up plotting the new parabola. But every one of those black vectors are identical. They all have the same length. They're all at the same angle to the x-axis. Now, in what's called column notation for vectors, I could say, well, the new coordinates is capital X, capital Y. And so what I'm doing is I'm translating the original coordinates, little x, little y, and I'm adding on a horizontal translation of 2 and a vertical translation of 1. And the idea of adding, when we've got them in column vectors, it's quite simple. We just add the x with the x and the y with the y, and we come up with our new one. So if I was to use parametrics then, instead of using little x and little y, I could say, all right, well, let's call the parabola the x value t, then the y value would be t squared, because it was y equals x squared. And so I'm going to add 2, 1, and I get t plus 2 for the x value, t squared plus 1 for the y value. So I now have the parametrics for the new parabola, and I can work that out by eliminating the parameter. Capital X is t plus 2, so little t is capital X minus 2. Sub it into t squared plus 1, and sure enough, we come up with that equation that we found before. Now, I'm not necessarily suggesting that that's how we would do this question, but what I want to show you is we could approach it using vectors, using that idea. Some definitions then we need to know, because like most topics, they sometimes have language that's unique to that particular topic. So there's a vector, PQ. Now the way we write it, PQ, and one notation is with an arrow on top. But the arrow is telling us the direction. So writing it as PQ is important. So we're going from P to Q. And so that's what we call the displacement vector. We've displaced from P to Q. P we often call the tail, and Q would be the head of the vector. Some other notations. The very first ones, we don't use that often. And that's just, we write the letter P in bold. And I guess the reason we don't use it that often is because if you're handwriting, it's very hard to bold when you're writing. So we don't use it that often. You see that more, I guess, in texts and things like that have been printed, and they can obviously make the letter bold then. More often we see it with P with the, what do they call those, a tilde? The little squiggle, whatever it's called, underneath the letter. So that represents the vector P. And as I said before, the beautiful thing about vectors is they're all unique and we can move them. So no matter where we move it to, the length or the magnitude will stay the same, and the direction or the angle it makes with the horizontal stays the same as well. The symbol for magnitude of the vector, and we've seen it before, it's simply the absolute value symbol. Because that's what we're doing when we're finding an absolute value. We're saying what is the distance from here to here. And often it's to the origin, because if we say absolute value of 5, we're saying, well, how far away is 5 from the origin? but it's all distance. So that is the symbol we use. The absolute value symbol means magnitude. So we could say the magnitude of P with a squiggle underneath, or the magnitude of PQ with the arrow on top. That's the size, the magnitude. How long is our vector? Opposite vectors, or negative vectors sometimes called, they're basically the same length, but the arrow's going in the other direction. Yes. So if PQ was equal to the vector P, then if I did write it the other way around, QP would be negative P. It's going in the other direction. So instead of going from P to Q, it's going from Q to P. So it becomes the negative of P. Parallel vectors, well, they're going to have the same slope. I mean, there's no different to coordinate geometry there. Lines that are parallel have the same slope or same direction. So those two vectors I talked about before, PQ and QP, they would be parallel to each other. This is an unusual one, the zero vector. So zero, just like zero as a number in maths, is an unusual number. Weird things happen. The same with the zero vector. Basically, it's a point. So I'm going from P to P. So I haven't actually gone anywhere. So it has no magnitude, but it also means it has no direction because you haven't gone anywhere. And so the weird thing is, it means it's parallel to every vector because you haven't gone into a direction, and so it's one of those weird properties of zero. It doesn't come up that often, but it's probably good we're aware of it. A scalar is just a fancy word for a number. So you have scalars and you have vectors. So vectors have direction, scalars don't. They're just a number. So lambda, well, I'm assuming that's a scalar, so lambda times the vector P just means the magnitude of P I've multiplied by a factor of lambda, whatever that is. A position vector is a very particular displacement vector. A position vector is when the tail is at the origin. So when you put the tail at the origin, that becomes a position vector. So how do we do our mathematical operations with vectors? So adding and subtracting. If you want to add two vectors together, you simply slide or translate the vectors so that they're head to tail. So there's a vector A. If I want to add the vector B, I just slide B so that the tail of B goes on the head of A, and that new vector I've created from the tail of A to the head of B is the vector A plus B. Now the beautiful thing about this is it means it retains the property of addition. So remember, you can add in any order, it's commutative. 2 plus 3 is the same as 3 plus 2. What's the same with the vectors? Because if I'd started with B and then added A, look what happens. There's B, add A, we get the same green vector. So addition still works as normal. So another way of expressing that, if I use the arrow notation, I could say, well, the vector PQ, there's PQ, plus the vector QR would be the vector PQ. So if you like, you could think of it as, I'm going to take out the common letter that's in between, push it together, and I get PR. Subtraction, I think of it as adding a negative vector, but instead of sliding it head to toe, basically you slide it head to head. So there's vector A. Now I want to go minus vector B. So we've got A, but then I'm going to go in the opposite direction. So you see it's the same vector, well, the same length, but now the arrow for the head is on the opposite end. So it became the negative vector. So I'm adding the negative vector, and we get, there's A, there's B, A minus B. There's the black one there. But something really interesting happens. What happens is they turn out to be the diagonals of a parallelogram. Watch. There's A plus B doing it one way. There's B plus A. You create a parallelogram. Got to be a parallelogram. Opposite sides are parallel. Well, one diagonal turns out to be the addition of the two vectors. The other diagonal turns out to be the subtraction. And that brings us to an important point. If ever you wanted to work out what the vector was, its actual position vector, when we slide it back to the origin, all you got to do is go head minus tail. So here, A minus B tells you straight away. Okay. Multiplication, well, we're only going to really multiply vectors by scalars. We're not going to do at this stage vectors times other vectors. So vectors times scalars. And as I mentioned before, that simply enlarges well, it might decrease depending on what lambda is. I mean, if it was a fraction, it would decrease. The size of the magnitude. So there's vector A, that would be 2A. Still going in the same direction, but it's twice as long. Half A, or actually minus a half A, I'm going in the opposite direction, but it's still parallel, and it's half as long. So all of these vectors will be parallel, because all we're doing is changing the length of the vector. All right, here's a question. So we've got a triangle ABC, and we're saying AB's vector A, AC is C, P and Q are the midpoints of AB and AC. R is being placed such that RC is twice the length of BR. So it's, in other words, it's sort of cut it in the ratio 1 to 2. Express BC and PQ in terms of A and C. So see, if ever we want to do it, it's just head minus tail. So BC would be the vector AC minus AB. If you imagine we completed the parallelogram, it's the diagonal of the parallelogram. And this one would be the subtraction one. So head minus tail, we get C minus A, would be that vector. PQ, well, PQ, head minus tail, P we were told was half of AB, and Q is half of AC. So it'll be half of C minus A. Compare these two vectors. Well, what can we tell from this? Well, we know that PQ is a half of the vector BC. Now this allows us to actually solve geometry problems using vectors rather than all the geometrical theorems. Because what property have we just demonstrated? Well, if we join the midpoints of two sides of a triangle, it's going to be parallel to the third side. That's what we just proved, because look, we've said PQ is equal to a half of BC. Therefore, they've got to be parallel. They're going in the same direction. It also means if I join those midpoints up, the length of PQ will be half of the length of BC. So now they want us to find the vectors BR and RC. Now, my diagram's gone off the screen, but you've still got yours there. BR would be a third of BC. And BC, head minus tail, is C minus A. So BR is a third of C minus A. RC would be 2/3 of BC. So it's 2/3 of C minus A. Show that AR is 1/3 of 2A plus C. So AR, well, AR would be AB plus BR. If I take the B away, push them together, I get AR. So now AR would be AB plus BR. Now in all of this we found that, well they told us, that AB was A. We found that BR was a third of C minus A. It's really just like algebra now. So I get A plus a third C minus a third A, 2/3 A plus a third C. So 8A is our, well, introduction to vectors, a bit of a play around with that.